So substituting in those equations for x2 and x3 in terms of x1 gives this here. So what we've got is x1i plus this structure, which is x2 in terms of x1j, plus this thing, which is x3 in terms of x1k, where now x1 is allowed to equal any real number. And this thing that we've got here, this is the solution to those two linear equations that we had. This is the set of all vectors that are perpendicular to both A and B. So on the picture, we have our vector A here and our vector B here. Remember, the set of all vectors that are perpendicular to both A and B forms a straight linear line in three-dimensional space. So this is the formula for all of those vectors, and as you let x1 vary over the range of all real numbers, you'll get a different vector along this straight line. So it defines, it's the solution space to those two linear equations. It defines the set of vectors that are perpendicular to both A and B. So you can stick whatever x1 you like as long as it's a real number into here, and you'll end up with a vector that is both perpendicular to A and perpendicular to B. Now, we want to select an x1 such that the modulus of this vector is equal to the area of the parallelogram defined by A and B, and we have here the formula for the area of that parallelogram. So we want to select an x1 such that if you take the modulus of this, it gives this, and we know that that only has two answers. It has the vector that points in this direction of size equal to this, and the vector that points in this direction of size equal to that. So this is one of those times where maths is wonderful. You can see how close the terms that we have up here are to the terms that we have in this expression here. So quite clearly, I hope you can see that if we set x1 equal to this here, and we're going to set it equal to minus because, of course, we know in the back of our minds what formula we want for the cross product. We don't want the negative of this, we want the positive version of this that's going to obey the right-hand rule. So we're going to put in x1 is equal to b2a1 minus a2b3, i.e. get rid of this denominator here, and we're going to make it the negative of that. So if you put that in, you'll get that you'll put your x1 in here, so you'll get minus of this times x1, so you'll get a2b3 minus b2a3i, and then the denominator will cancel with this, and you'll end up with the negative of this times j, so you'll get minus a1b3 minus b1a3, all in brackets with the minus in front of it, and then finally here you'll get the denominator cancelling, and you'll get minus the thing in the brackets here, so you'll get plus a1b2 minus a2b1, and I've specifically written this in the way that we saw the formula for the cross product earlier in the first part of the video. So if you think about what the size of this vector is going to be equal to, well, it's going to be equal to each of the components squared, added together, and then the square root of that. So you want to take this bit squared, add it to this bit squared, and add it to this bit squared, and take the square root of that, and you can see that that will give this formula here. So this bit that I've underlined in yellow is this bit that I've underlined in green gives this bit that I've underlined in blue gives this bit. So this vector here is both perpendicular to the vector A and the vector B, and it has size equal to this. Now, if you took the negative of this, so put a negative sign here, turn this to a plus, and put a negative here, which is what we would have got if we just substituted x1 is equal to this without the negative sign here, that vector will also have modulus equal to this, but it will be the vector that is pointing in exactly the opposite direction to this one here. The final thing that we need to show, therefore, is that this is the one that obeys the right-hand rule. This is the one that is pointing upwards on this picture. But before we do that, let's just cover our sloppy algebra that I talked about in the last video. So our sloppy algebra, which wasn't valid for all cases, has given this result here. We now need to prove that this result does hold for all cases, even though the method used to derive it doesn't. So we know it will always have modulus equal to this, we just need to show that it will always be perpendicular to the vector A and the vector B. So we just need to take this and dot product it with A and dot product it with B and show that the result is always going to equal 0. So let's start by dot producting it with A. So we just need to take each of the components and multiply them by the components of A and add it all together. So here is this done here. So A1, the first component of the vector A, multiplied by the first component of our answer is this bit, plus A2 times the second component of our answer, which is this bit. I've just swallowed the negative sign into the brackets, so it's become B1 times A3 minus A1 B3, and then finally we need to add that to the third component of the vector A multiplied by the third component of our answer, which is A1 B2 minus A2 B1. Expanding this out, and you get A1 A2 B3 minus A1 B2 A3 plus A2 B1 A3 minus A2 A1 B3 plus A3 A1 B2 minus A3 A2 B1. Now, what I've done here is I've underlined the terms that are going to cancel. So this term here, A1 A2 B3, is going to cancel with this term here, which is the same thing, just written in a different order. It's A2 A1 B3. So that term cancels with that term. Then look at this term, minus A1 B2 A3. That cancels with this term here, which is the same thing, just written in a different order. A3, A1, B2 with a positive sign in front of it. So that one cancels with this one. And finally, the ones in red. So we've got A2, B1, A3. That will cancel with minus A3, A2, B1. Again, the same thing, just in a different order. So all of this will cancel, so you'll end up with 0. So clearly then, when you dot product this answer with the vector A, it will always give you 0, and nothing here relied upon multiplicative inverses existing. All of this algebra was valid for all cases. So even though the mechanism, the algebra used to derive this result was dodgy, the actual answer isn't dodgy. It applies for all cases. Now, finally, we just want to do the same thing for the vector B. So if we dot product this with the vector B, we get B1 times A2 B3 minus B2 A3, which is this, plus B2 times, again, I've swallowed the minus inside the bracket, so it's B1 A3 minus A1 B3, plus B3 times the third component of our answer, which is A1 B2 minus A2 B1. Again, expanding this, and the same thing's going to happen again. So expanding this gives B1 A2 B3 minus B1 B2 A3 plus B2 B1 A3 minus B2 A1 B3 plus B3 A1 B2 minus B3 A2 B1. And you can see that this term here, B1, A2, B3, is going to cancel with this term over here. It's just the same thing written in a different order, so it's minus B3, A2, B1. This term here is going to cancel with this term, B1, B2, A3, B2, B1, A3. This one's got a negative, this one's got a positive, so those two will cancel. Here we've got minus B2, A1, B3. Here we've got plus B3, A1, B2, so those two will cancel as well. So again, this dot product will always equal 0 no matter what these numbers A's and B's are equal to. So again, this answer will always be perpendicular to the vector B, and nothing here relied upon any multiplicative inverses existing. So all of this algebra is always valid. This result, this vector here, is always going to be perpendicular to the vector A and the vector B, and it's always going to have modulus equal to this thing here, the area of the parallelogram defined by A and B. So again, I'll stress, even though the algebra that we used to derive this result relied upon all of those multiplicative inverses existing, and therefore it was very dodgy because they wouldn't always exist in some cases, the actual answer that you get does apply for all cases, is valid for all cases. So the answer isn't dodgy, even though the mechanics used to derive it was.